Lev Ioffe on simulation of physics problems in faulty quantum computers.
Let's begin lecture 2. I wanted to start with a quick summary of what we discussed last time, namely that qubits, although they are intrinsically nonlinear oscillators with a small nonlinearity, if we treat them gently, then we can describe them as spins, which one half, which therefore take only 0 and 1 values. And we have a few natural Hamiltonians that we can realize with these spins. Namely, statically, we realize this simply exchange coupling between the spins. If we go bumping, then we, in the rotating wave approximation, we realize also this coupling with arbitrary phase, which is at our disposition. Of course, this, as always in condensed matter, this is not the full story. This is just approximation. What is the main approximation that we do? As was clear last time, what we do, we integrate out all the states 2, 3, and everything else of these nonlinear oscillators, and reduce the problem to that. But when we integrate out, of course, these results are not exact. These effective Hamiltonians are obtained, well, in the linear approximation over this in this procedure. And I realized yesterday when talking to some people that it's really worthwhile to discuss what are the remaining terms, namely what are the corrections to these effective Hamiltonians, because they are not negligible. I remind you that the parameter of all that we do is always the gap, effective gap to the higher state, which in our case is J, which is this effective interaction, divided by delta E. And delta E is what we call an harmonicity, which is the difference between between the distance between state 2 and 1 and the state and the distance between 0 and 1 states. So that this, as I derived to you last time, this is nothing but the half of the charge of energy. Okay, so this is a parameter. In the leading parameter, we have
sorry.
Yes.
But this is a big parameter. Well, we have weakened harmonicity.
Weakened harmonicity, but J is even smaller. Otherwise, the whole thing breaks down.
Okay.
So if you remember in numbers, I was giving you that J, we have to keep, well, let's say 20 megahertz in reality, and delta E is typically 200. Well, you know, you can negotiate 250 maybe if you bargain well with the experimentalists, but you cannot go much further.
And just to make sure that we're on the same page, and J, we control it just with this control coupler.
Here it is controlled by coupler, and in the second it's controlled by the pump. So strength of your pump. Okay, so in principle we can make J small. That's very easy. It's much more difficult to push it up. So now I would like to discuss what are the leading corrections. So that, and then I will explain why in some cases these leading corrections are not innocent at all. So the leading correction, one of the leading corrections of the two, comes from the process. Imagine that we have two qubits, two spins up next to each other. Then, if there were two spins, if there were really two spins, then the process in which I act with sigma plus, sigma minus on the these two sides will give us identically zero, right? Because I cannot move the spin further. However, because they're not real spins, we can have a process in which we go from this side to the side, from this configuration to the state, what's this, 2, 0, right? And of course it's out of our Hilbert space, so we're going to integrate this out. But this process exists. What it leads to? It leads to the fact that the energy of, so if we go sort of, we can imagine a virtual process that goes to this state. And then back. So that returns to the Hilbert space, to the same Hilbert space. And therefore it tells us that the energy of the state in which both spins are up acquire additional negative contribution with the amplitude, which is J squared divided by delta E, where delta E is our informaticity, that is how much we pay if we go to state 2. Yeah.
Excuse me?
Yeah.
It's not clear to me what kind of action you do with this.
What kind of, sorry?
What kind of action you do with these two, sigma plus, sigma minus? It's 2 times the same operator and acting on.
Oh yeah. Sorry, I should put J. I'm very sorry. I just meant some other side. So it's one. There is side I, side J.
Well, why first is 0?
That if it were real spins, it would be 0. That's what I want to say. That if we just limit ourselves to Hilbert space, then this will be for spins 1/2, right? Just literally 0 because we cannot do that. But in reality, it's only approximation that the spins 1/2. So this operator acts and it just gives you something which costs energy. Notice that our transmode, and actually that is a very unpleasant feature of the transmode. It has negative nonlinearity. That is, and that is due to the fact that we are talking about cosine, right? Cosine potential has a 5-4 term, always comes with minus 1.4, right? In cosine, compared to the first phi square, right? So nonlinearity of the transform is always negative. In some sense, we don't pay for the energy, we get it. So that's a very unpleasant feature that will be important for something else, but it means at the moment that what at the moment, the only thing that's relevant is that it's minus, so that we keep the signs. So that means that there is effective interaction which is, well, and there is a factor of 2, probably, well, well, I don't guarantee all the factors of 2 correct here, but roughly speaking, it's like that. So here, I introduce a quantity which experimentalists like very much, which is occupation of the level 1, which is, of course, in terms of the sigma z operators, it's nothing but this. So it's very convenient when, as you all seen in a moment, when we will discuss systems with many excitations, it's very convenient to think about occupation of, and they call it also number of photons in the system. Because if you view this collection of transons as just one very big resonator, then it's number of excitations, number of photons. They also say that's an experimental jargon. So I will try not to use it, but that's experimental jargon that they like to use. Okay, so but in terms of normal spin models, what we of course can rewrite this Hamiltonian as this. And yes, I maybe didn't emphasize enough that all this process, that this additional contribution only comes if we have 2 spins in state 1. So that's why this product n times n, that is, we get this additional contribution to the energy only if both sides are occupied. Okay, and that of course is nothing but the relevant term here is the sigma z interaction, sigma j interaction, plus of course some fields which act on individual spin, but these fields proportional to just the sigma z operator, but that's just shift of sigma z, of the big sigma z terms that we always have in our system. So it's completely irrelevant. So what we get from this argument that in fact we always have not only, at least in this way of doing things, we have not only sigma xy interaction, but also a little bit of this. How little you see here. So for typical values of j over delta E is typically 1/10. So you see that typically we get about 5 to 10% of this interaction with respect to h1. It's very difficult to get to the isotropic limit that will be practically impossible. But in a bit of the Z way. All right, now, but that's not it, unfortunately or fortunately, because there are other processes which appear in the same order of perturbation theory, namely, so now we dealt with this, so let me think how to. Yeah.
Can I ask at this point? So in principle, what you could do, you could drive this system.
Oh yeah, you mean pump?
You could
Pump,
use some
if I do
external
pumping,
then
these terms do not appear.
Huh?
If I do pumping, these terms do not appear.
Why not? I mean, if you could just pump between this what you call 1, 1 and 2, 0, right? Then you would get some term.
Yeah. For this, I will need to pump at that frequency, right?
Exactly.
Yeah, sure. Then I can do everything.
Yeah, but why are you not using this pump essentially to eliminate that term?
Well, that will be extremely complicated system. That is, I do static and pumping, right, and try to compensate one with another. Yeah, in principle, I could do much more complex.
Or is something that you're just pumping inducing some higher order occupation?
Right. Yeah. Then
probably.
Yes, but don't remember that high order occupation always doesn't come free. What you pay is that at higher energy states, you have much larger decoherence. So if you start to admix higher energy states, you pay. So yes, you can do things, but the cost can be quite prohibitive. Well, okay, so but let me tell you what you get for free here, whether you want it or not, is another process. Another second, so that was my first process. And the second process is the following. That suppose I have two spins, but at some distance, at distance 1 from each other, then, and this spin is in state also up, and that's crucial. So I have I, J, and sorry, let's say that I have states spin I plus E, its neighbor, and spin I minus another neighbor of the same I. Then I can have a process in which I move this excitation to this, if I move this excitation to that spin, so that I form state 2 here. So in other words, I started with something like 0, 0, 0, 1, 1, and then I go to the state 0, 2, 0, and then of course it's out of Hilbert space, right? Similar to what we discussed before. But then I can go back to my Hilbert space, but to the state which is 0. Sorry.
1, 1, 0.
1, 1, 0. Yes. Thank you. So that means that there is, and that's additional contribution to the Hamiltonian, which is described by the effective Hamiltonian, which contains sigma plus I plus E n, because it only happens if the intermediate state spin is in state 1. Like this. And the coefficient is the same that we, again, that's the J squared process, right? Because we move twice. And we pay energy delta E, like before. So what is this, what is this new character? Well, first of all, it happens, as you realize, not only on the line, but if we have two-dimensional array, it also happens as an exchange between these two sides. because it's really important which side is which neighbor. And second, it contains this again, it contains this intermediate it has this intermediate sigma z term in between. So what can this term be relevant for? One important consequence of this term is for one-dimensional chains. Our effective, for one-dimensional chains, our effective Hamiltonian is the same as before for the nearest neighbors plus JZZ for the nearest neighbors that we just discussed. So all these terms are integrable. Now we have two new, now we have this term, which I will write separately because it has these two contributions. One is, well, actually it's the same JZZ interaction, so, but I will ignore it, I will write it as if it is a different coefficient. Sigma plus I, sigma Z, sigma I plus E I. So this term, in fact, does not violate integrability because, you know, if you do the transformation from spins to fermions, then the spin is sigma plus is C dagger times the product of sigma plus on the right, sigma z on the I j minus I. So this, so when you put this into this Hamiltonian, you immediately see that this term sigma z cancels with extra sigma z, so you still get the free Fermat hopping. So that's still the same C dagger C. And now it becomes the same fermions which hop around. However, the second, this one is not so innocent. Because here we have the non-nearest neighbor hopping in terms of the, sorry, non-nearest spin interaction, and of course always plus dimension contribute. Forgive me that I'm not writing. So this term is not integral. So in other words, if we try to make 1D chain from our transnodes, then naturally we always have some amount of non-integrability. We cannot make purely integrable system. Always integrability will be broken, a little bit. Yes?
Well, I missed how this last term appeared, so...
From one.
From...
One.
Ah, yeah, okay, I see. Yeah, okay. Yep. Yep, thank you.
Yep. All right. So that is all that we have. What I want now. Of course, what I can say about the corrections. Of course, you understand that what we just did with you was a leading non-correction order in J over Z J over delta E. We get these two terms, but if we continue, we'll get more and more and more. So that the question is, what is the accuracy that we need? But from the viewpoint of introducing new physics, let's say in this break of integrability is definitely a new physics which appears, and that's why this term is relevant. And probably the higher order terms, well, I don't know what could be important from what could be something which is small but still relevant. I don't know. Maybe there is. Okay, good. Now, I want to. So that's what we have. The essential Hamiltonian that we deal with. Now we can ask if we are limited just with this very trivial, basically ferromagnetic interaction in xy plane plus the corrections, which on a square lattice. So naively, what we get is we have ferro xy interaction plus square lattice. And, well, doesn't seem that we cannot get so I would like to argue that this is a wrong conclusion, assuming that we are willing to go to higher, to sacrifice some of the qubits and reduce the interaction. Namely, we can do one more step in integrating out degrees. Irrelevant degrees of freedom. And then we can get very interesting problems. What I mean is the following. Look, what was the general concept here? That we started with this complicated cosine potential, but we integrated all the levels out except the first two. So we reduced the problem to the spin. We have this interaction. And so, but then we find that interaction is not so interesting. But we can go further and do, for instance, the following. So start with our spin model, which with the spins on square lattice, and I wrote just for the viewpoint of presentation, I rotate mentally the square lattice, and paint it in black and white. So it's, at the moment it's the same spins, and everywhere here I have my sigma plus, sigma minus interaction that God gave in the form of Charles Neal give to us. So, so we have this interaction between the spins, and I just mentally rotate. But now I do the following evil thing. I now apply easy, and that's very easy for me, sigma z, large sigma z field, only on sides which are what? Oh, circles. So experimentalists will say that I detune so all my frequency, remember that in fact I always have the large fields applied on all sides, because this is what my omega 01 is nothing but a large field applied to each spin, and I don't care about it if the spins are the same, and all processes conserve the magnetization. But I start to care about it if some fields are different.
Sorry,
So yes.
We apply to every spin or?
Oh no, only to this. I don't know. White, I don't know. Zeros.
Okay.
How do you call it?
Sorry.
So what I want is to apply, and I consider only the situations, only the states in which occupation for these sites is 0. That is, these sites are empty in the language of experimental physics. Then what I have is, and so my life, my real quantum degrees of freedom are only the sigma on the sides which are the node-byte crosses. So what is then the effective Hamiltonian on the cross sides?
I'm sorry.
Yeah.
So you mean that you apply so strong field that
Well,
fixes?
yes, so I apply field which is larger than J.
Yes.
Yeah. Yeah. So then what I have is effective Hamiltonian for the crosses. What are the processes which are relevant? That's again virtual process in which I take the, which I act on the, let's say, side which belongs to one cross, and then, so that brings me out of the Hilbert space as before, and then, so let me, how do I draw it? So, yes, so suppose I start with this cross, I move the excitation here, that of course I pay this energy H, and then I move it here. But notice that in this way, I can also move it here as the second step. So this is the first step, and this is the second step. I can move it either to the side which is, let's imagine this bigger lattice. So if I imagine the lattice of my cross side, of these cross sides, which are the only sides that I would like to leave after integrating out the zeros, then on this effective interaction will be the transfer of magnetization between the between near-ring crosses, but also the transfer of magnetization along the diagonals. Because I can move, this first step is here, but then I can go either here or there. Right, so both of these crosses. Now notice further that if I move to the nearest sides, I can do it in two ways. I can first move somewhere here, and then here. That's the first process. So because here I also have, of course, 0. Or I can move this way. Whereas if I move along the diagonal, I can only move in one way. Therefore, what I get is the effective interaction between the cross sides, which is sigma plus, sigma minus, between the nearest neighbors, and the same term, but which involves the coping. So E is nearest neighbor here, and E prime is the diagonal. Now the sign, as before, J effective, of course, is J squared divided by now, instead of delta E, which was the intrinsic anharmonicity, it is this field H that appears here. So of course I lose a bit, quite a bit, I lose in the value of the interaction, but what I achieve is, yes, and of course this field, as before, can be positive or negative, I don't care. So I can generate in this way antiferromagnetic coupling on a lattice with diagonals. Now, in fact, this coefficient 2 that I try to convince you is very lucky because in this problem we know from the numerical simulations that if we denote this as J2 and this is J1, then as a function of J2 over J1, there are different phases, and that's quite simple to understand because if you have very strong coupling between nearest neighbors, you form normal antiferromagnet. If you have very strong coupling between the diagonals, you form antiferromagnet on these sublattices.
But how can you control?
No, you just say you cannot.
Okay.
You cannot.
Okay.
But the critical point is
Exactly 1/2.
1/2. That's just a luck. Yeah.
And why don't you go another nearest which is going down?
Sorry.
Like the one is parallel and another one down in square?
Yes. So there is all of them. So here we have all interactions, right? That's what you meant, or you meant something else?
Yeah, like I said, the first term it's counting like from one side to another nearest neighbor.
Yes.
In two ways, like in the middle and then.
Yeah. So you mean that it can go left and right? And
Yeah.
And of course, yes. Of course. So on all bonds, to avoid double counting, I would prefer to count each bond once. Otherwise, you have to write this 1/2 and say. So for each bond, for each horizontal bond, for each vertical bond, I have this term.
Mm-hmm.
And for each diagonal, I have this term.
Yeah.
And in this way, it's much easier to take care of these factors of 2, which are always extremely confusing.
Mm-hmm.
So this problem is in fact quite interesting because here there is something unclear what it happens. Numerical simulations, I think, prefer, point towards formation of just a critical point, but I'm not the person who can judge the validity. Yes, please.
What is your y-axis?
Temperature.
You mean critical temperature?
Yeah. So because there is a trivial antiferromagnetic phase here, trivial antiferromagnet on independent on both sublattices here, because if you say that this is the strongest interaction, then you form an antiferromagnet like that, and so independent antiferromagnet on these two sublattices. So it's both phases are sort of not interesting. But here what happens is interesting. Even if it is just a critical point, it's still not trivial. But I'm not in a position to judge if the numerical simulations which show that it's just a point, not a phase, right?
Yeah.
So alternative could be that in fact there is a phase which is formed. And so the work that I know claimed that there is no phase, it's just a critical point, but I don't know.
But this is still like purely numerical.
Yes.
Okay.
Yeah.
What is the typical size of the system for this simulation?
It's some
20.
No, it was Monte Carlo. Maybe not Monte Carlo, I forgot how it is. don't. Okay, I will not say because I don't. I think it was tensor networks. Now that I start to recollect, and the size is irrelevant because in size is technically infinite, right? But the question is, what is the effective size of the Hilbert space that they kept in these tensor networks? And that, of course, I don't know. Okay, so you see that even if we start with this supposedly boring interaction with a little bit of ingenuity, we can generate interesting problems. All right, now I think that I'm done with this part. Okay, let me discuss the next very important conceptually part, which is the measure. Because here we are really very different from normal condensed matter. We can do things which they cannot even imagine in their dreams. So because such. All right. So, of course, the main difference from condensed matter is that we can measure individual qubits.
Sorry,
Yeah.
Go too far. So, what I have to carry on from this, from the previous topic, when we actually fixed this, fixed points and we had.
No, I just was the first example that we can do something non-trivial. Even though because when you just ask a mathematical person, you look at this Hamiltonian, it seems that the ground state is trivial, ferromagnets, so what we are talking about. Go back to sleep, right? So I'm saying, no, wake up and something non-trivial. In condensed matter, normally we do not worry about the effect of measurement on our system because we do not measure individual spins. We measure very little, but many spins. And here we measure individual qubits, and therefore there is a conceptual question, so that we have this spin, which is equivalent to the transmon, to these first two levels of the transmon. So we want to, in some sense, look at it, right, and measure it, and say whether it is in state 0 or 1. But of course, when we look at it, we destroy the quantum mechanics tells us that we completely destroy coherence, right? And that's normal. No but that's exactly what we want. It's not a big deal that when we measure, we of course destroy coherence. only to be expected. But now comes the most non-trivial part. We should not destroy the coherence when we do not measure. So how do we do that? Even in principle, how the system knows if we will look at it or it does not. What is this n? Now, I mean, so that to understand that the problem is very non-trivial, is that we want to measure, preferably at the times which are less than 100 nanoseconds, and we want the coherence times to be larger than 100 microseconds. So in some sense, we have to switch off our measuring device to the level of 10 to minus 3, or actually even better. So you see, if we just look a little bit, it's very bad when we do not want to measure. So the question is, what is the switch which has on-off ratio which is better than 10 to minus 3? It's a very non-trivial question. Yeah.
Just tau m is measurement, right?
Yes,
right?
yes.
Okay, and this like on-off measuring 10 to the power minus 3 is like a tau m divided by tau.
Yeah.
You mean that? Okay.
So here we destroy completely coherence over this time, preferably less. But we want that when we do not measure, we switch off.
Yes.
We do not destroy coherence at these times.
Okay.
And it's better to be 10 to minus 4, because we don't want this to be a main mechanism for the coherence. We have another mechanisms.
Okay. So you mean you just want tau m to be much smaller than tau m2, and that's it?
Yes, no, that's of course, but it means that the switch that tells us whether we look at our system or not has to be on-off ratio of 1000, or better 10 to 4.
Yes, okay.
So when the switch is off, it's really off. It's not just 10% or even 1%.
Okay. Oh.
We do not want even to peak at our system.
Okay, probably let me reformulate. You mean by measurement with a coupling to some external something, and you want this coupling to be very small?
Right,
okay.
yes.
Okay.
Yeah.
Now
and so I have to be able to switch off this coupling to environment with this enormous accuracy.
Yes.
So even a tiny bit is very bad. And that's a main problem. So how do we do that? And what is the sort of the physical suite, the physical mechanism that ensure conceptually what is a quantity that we can vary so much? 10 to 4 is a very big number. And normal condensed matter, if you suppress something by 10%, it's already a big effect. But here we need 10 to 4, which is enormous. So the idea is that we take our transmon and couple it weakly to the normal linear resonator. So, and the conceptual idea is that it's the number of phonons in the resonator is our switch. That the number of phonons during the measurement time is, I don't know, if about 10. And when we have no measurement, we have to suppress the density to the level of 10 to minus 3. And that's our switch. That's the quantity which varies by 10 to 4. This is very non-trivial because we need to empty this resonator completely, not just more or less empty, just completely empty. Yeah.
One of them is like capacitor.
This is, sorry. Yeah, absolutely. That's our transmon, and that's that's really a linear resonator. I'm very sorry. Now, practically, not practically, the second part of that's the sort of the main conceptual idea that the parameter which controls this on-off is the number of photons in this resonator. Now, the second part of the idea is
What is 1,000, one of the 1,000?
number of photons.
It is a probability to find the single.
Well, just if you A dagger A. That's what you will call a number of photons. Average.
Why it controls the coupling?
No, I will explain now how the dephasing works and why. But the main point is that there is something we can vary by 24. That was the main, very non-trivial part, because there is nothing else that we can vary so much.
But will you explain how
Well, just
this quantity can be varied?
How this
How
quantity
can be suppressed so much?
Yeah. So that is actually very not difficult at all once you realize what you want to do. So the next part of the idea is that we have here our beloved qubit frequency, and we have here the resonator frequency. And resonator frequency is very different from the qubit frequency. It is much larger than everything. It's coupling between them, actually much larger than coupling between them, much larger than delta E of the qubit. So it's really very far. So, and in fact, the best readout schemes were achieved for the resonators, which are in which resonator frequency even slightly much larger than qubit frequency in absolute units. That is, that not only the difference is large, but let's say Michel Devoret group in Yale had the resonator frequency of 10 gigahertz and qubit frequency around 2, and they had very good result. So it's really very far away. So why it's relevant? Because it means that the process in which the excitation is simply transferred from the qubit to resonator is completely impossible. That is, there is no such process in which we destroy the excitation in the qubit and create a resonator, because the frequencies are so different, the coupling is small, it doesn't happen at all. Now, but what then, how they interact? They interact due to the fact that there is nonlinearity in the qubit, and therefore there is effective interaction between the resonator and the qubit, which is sigma z qubit, sigma z qubit, some interaction constant, of course, times A, dagger A in resonator. This interaction just means that the frequency of the resonator is slightly shifted by the state of the qubit, whether it's 0 or 1.
But I mean, physically, how this coupling is achieved?
Or just a capacitor, right? And because you have some virtual process in which the photon jumps into the qubit, and qubit is nonlinear, you get this in the second order perturbation theory.
Okay, yeah. Okay.
So now, so now you understand what is the idea of measurement, because the idea of measurement is that we expect that the resonator frequency is plus minus 1/2 G, depending on the state of the qubit, because of this term. And so that if we, well, naively you will say that if we measure the response of the resonator, instead of the peak at instead of the peak at resonator frequency, we see these peaks in the either shifted slightly below or above. And so reading out where is this peak, we see the state of the qubit. Yeah.
Why is the non-linearity important for this coupling to work?
Oh, because if it was if everything was linear, there will be no shift in the frequency depending on the state of the qubit. Linear system doesn't care exactly what is linear system. That you have, if you have more than one mode, you put another one mode, but the frequency of another mode doesn't change. Like in normal electrodynamics, you have a radio wave at 1 gigahertz for the cell phone frequency, and you have 50 gigahertz, 50 hertz here, and they don't talk at all, right? So electrodynamics is a completely linear thing. It is only due to, and no, the only source of nonlinearity is the qubit. You could have put some nonlinearity here as well, but that just makes it more complex to design.
But within the qubit, I only have one transition, so I don't really see how to.
Oh, no, you have to include virtual process in which you go, not even this virtual process in which the excitation jumps into the qubit and it, how do I say, okay. So let's, so we have, for the qubit, we have normally this, where this delta E. Right, this is our nonlinearity. And we also have the term which is, let's call it G for a second, A dagger B, which is this term in which the excitations hop between the resonator and the qubit.
A are the photons. And
Yeah. So A is my resonator and B is my qubit. So you see that, and you do this when I diagonalize, well, of course I have also omega R, right, A. Now when I diagonalize the linear part of the Hamiltonian, I have some admixture of A to B. Forget about nonlinear terms for a second. Diagonalize the linear part. I mix A and B because I have this interaction. And so now when I put this new sort of, what I get after I diagonalize, I will get B is equal to the dagger is B tilde times the coefficient, let's say cosine theta, B tilde plus sine theta A tilde, right? And the same for A. So when I express this B in terms of correct eigenmodes, B tilde and A tilde, I start to generate many different terms. And in particular, I will generate the term which is B tilde dagger B tilde A dagger tilde A, with the coefficient which will be sine product of this sine squared, right? So, and this is exactly the term that I wrote here, because B dagger B is the correct operator which measures the state of the qubit, and this is the number of photons in the resonator. All right. So very good. Yes. So now, so you see that this interaction allows you to measure the qubit. Now, but why it also leads to the dephase? It's quite clear, because if we have some arbitrary number of phonons in the resonator, that fluctuates. Photons. And the number fluctuates because they come from, well, they come from outside line somehow, and the number is might be different, and therefore the qubit sees it as a fluctuating field. Okay, so that provides dephasing immediately. So in order to avoid this problem that sometimes we have a photon, sometimes we don't, we need to completely empty this resonator into outside line. Now, is it possible? It is possible if the energy, so the average number of photons is of course exponential of the frequency over temperature. So if frequency is quarter of a Kelvin, which is and we can keep temperature and omega r over temperature larger than 10, then it's okay. So we need to keep the temperature sufficiently low so that the exponential, so that the number of photons is below our limit, which is about 10 to minus 3. But you see that it means that we have thermalized extremely well our resonator. That the danger of having spurious, of having effective temperature of the resonator sufficiently high is if the temperature of the resonator is even slightly higher than our limit, then we immediately get very large dephasing due to this resonator photon. That's why it is very advantageous to keep the resonator frequency high. Let's say half a Kelvin instead of quarter of a Kelvin, so that it's empties better. Yes?
What can give rise to an effective temperature in the linear resonator typically?
Well, that's a very, very unpleasant question. Because if we could have just a resonator and then outside line, then okay, you say that you can thermalize a line by making a good contact with your cryostat. But unfortunately, we have to get these 10 photons out, right? And so we have to amplify them. And that means that in reality, what we have here somewhere is a very, very evil thing, which is called amplifier. So, an amplifier, as some of you certainly know, produces a lot of noise. So, if we do directly what I do here, we will not have any measurement whatsoever. It will be a complete jump. So what in fact we have to do, we have to jump through many, many hoops on the way. First, we put here additional resonator, which is called Purcell filter, which only allows the signal at frequency omega r. So it cuts off everything else. But that's by far not sufficient, because this amplifier is really bad thing. And so on the way, we put many evil devices, which are called circulators, and not one but many, usually 3. So the circulator has a property that the signal propagates only in one direction. So it's sort of like that the microwave signal goes only in clockwise in the circulator instead of going both directions. So as a result, so each of them basically provides about 20 dB of decoupling between in and out. So when we put 3 of them, that's roughly speaking good enough. Yeah, sorry.
It's more or less bicycle system, yeah? So
Yeah,
when you're talking about it goes.
Yeah, no, it's terrible system. Will not, and of course, it's not the solution that will be good for a big qubit systems. But that's how typically people do that. Because each circulator is a huge thing. It's like that. Have you seen it? You have probably seen it, right? Even though you are a theorist. It's like this. It's the size of a quarter. Even if it's small one.
And it's all on the lower stage.
Yeah. So,
And how then we can be sure that there is any kind of thermal distribution? Like
I'm sure that there is no thermal distribution. That's what
your office exposed.
Yes, that is exactly what I wanted to say next. That if it was thermal distribution, it would not be a problem. But unfortunately, these circulators has another evil property that they provide this good decoupling only in a very limited range of frequencies. And we know experimentally that there is a lot of high-frequency noise which comes in and disturbs our system, and that's a very big problem for all good redoubt. And then different experimentalists have different ways to deal with this problem, and they usually don't want to talk about it. As our friend Michel once said, that maybe it's not political. No, it's recorded, so I cannot say what.
And what about like using parametrical amplifiers?
Oh yeah, that's parametrical.
Like just some like the one.
Yeah. So that's parametrical amplifier, and then there is a real amplifier filter. So they all produce noise. Actually, I think it's even a theory that you cannot have the amplification without noise. Okay, so that is the sad truth about redoubt, that it is possible, but with enormous cost.
Yeah, sorry, I probably missed a little bit. Yeah. So how we actually redoubt? I mean, right now you just introduced the...
So what we do is, maybe I should say that, here, or let's say put here, we put the pumping signal, we inject photons, we measure the reflection, we distinguish between these two transmission coefficients, and then we say that if we see that, it is state -1, if we see that, it's state +1. In fact, we do slightly different, but for the cartoon it's enough.
Okay. Yeah. Thanks.
Yeah.
Okay, probably you can give some comments about why should we choose 10 and 1.
10 and 1 and not, let's say, 100 and 1, right? Yeah, that's a good question. And the reason for that is that imagine that our qubit is not just 2 levels, it has many other levels here, and here moreover, when we go to the top, there is a chaos in these levels. So what we want always to ensure that this resonator, high levels of this resonator are not in resonance with these high levels. Because if they are in resonance, even though the coupling is higher order, we will get transference photons from a resonator into the qubit. So practically, it means that we cannot have any energy here, which is so n times omega r should be less than I don't know, half a g or something like that. Otherwise, we start to transfer energy somewhere here where we have absolutely no control. And not only that, even if its probability of this process is rather small, once we sort of kill the qubit by putting it very high up, it will live there and will have some chaos and it will do enormous damage on the surrounding qubits. So it's really a very, very dangerous process. So we cannot afford it even if there is very small probability. Yes.
That's a little bit. So you said that you have your qubit energy scale. You have omega r, which is now 10 times larger or something, or 5 times larger.
No, that is they were in Yale. What we have at Google and most other people have, let's say, qubit is 5 gigahertz and omega r is 7. So it's not that different. But what I was saying is that Michel group in Yale achieved extremely good result by moving these frequencies really far apart. And yes, and there are different ways to improve this scheme, and there were very good results from Japanese group recently who achieved excellent results by just improving this problem of how to by just doing always the same, how to make sure that the photons get out and the noise doesn't come in. And there was also very good result scheme by Wolf. But also they were in Etihad. So, but it's, what they do in different combinations, they put more filters, more resonators here. And so we can discuss how it works, but I don't think it's appropriate.
Speaking about which fidelity.
Okay, so which group do you now ask about? Because
I mean, you mentioned the best, like.
The best.
Group or...
Yes, Yale group. Let me. So 99, right? So I think the fidelity of Yale group was P Yale, right? Was 0.99 with maybe third digit. In Japanese, Rihan group demonstrated even something like this. Volarov group, I don't remember. But sort of in this ballpark. But you see, the main, you should not look at just at these two numbers, or just at these numbers. You should also look at the measurement time. Because if you measure too long, it's not good either, because the qubits start to decay. So, I don't have, if you're interested, I think I have a plot which shows all possible groups and all possible results. I can show it tomorrow, but I don't have it handy with me. So that's if you're interested. Okay, so now that was about difficulty. However, I would like to explain now that there is a silver lining with all clouds, that as a result of this effort, we can get access to the quantities which are completely impossible to access in normal condensed matter. So, yes, so of course we sort of, as I explained, after all this effort, we really measure sigma z. That's the direct result. But we can apply sigma x rotation on our qubit first, and then to any angle alpha to unknown state of the qubit. Oh, first, and then measure. In this way, we can measure the qubit. Effectively, we can measure any operator, sigma, let's say n, or any n. So that is not so remarkable by itself, but look what we can do with that, which is completely impossible otherwise. Yeah.
Once again, by blindness exponents, you mean what kind of operation?
What kind of
Letting
operation?
it evolve under sigma.
Yeah, so what we have, so remember that our individual qubit, we can apply the external field, which is this, with which is in resonance with the qubit frequency, right? And that in rotating frame just means that we rotate the qubit around x-axis.
Ah, yeah, okay.
So that, which is exactly what I wrote here.
So this is like turning on the field, let it evolve.
It's turning RF field.
Okay.
So at exactly the qubit frequency, so we rotate it where it was. And we have, of course, z rotations which come from nothing because it always sits in the Z field. And combining these two rotations, we can rotate where we want. And then we measure it, and as a result, we measure the qubit in absolutely any basis, and that's the most standard things that one can do. Now, so suppose, now what I want to argue is that in
Can I
this...
just ask one thing?
Yeah.
I'm kind of confused. Let's say that you would like to understand about some property of the ground state. You prepare somehow.
Yes, so that's what I want to explain. Is that
Okay.
Just a second. So now what I would like to explain to you is that using these two things, we can measure the correlators of the spins in, let's say, the ground state of this sort, which are completely impossible, which looks to be completely impossible, even if you look at sort of standard textbooks, you will see that you can only measure the operators which are Hermitian, and this is sort of as far from a Hermitian as one can be. It's not anti-Hermitian, it's just nothing. So how we do these things? So suppose we first we start with our ground state, and we first apply sigma x operator, which we generate in this way. That's not difficult. Or sigma plus operator, we just move the state to 1. But then we measure, let's say, sigma x. And then what does it mean? That we really evaluate this quantity. That is, we apply this perturbation, or apply this drive. Then we measure. Of course, once we apply the drive, we get a new state, which is sigma, which is sigma plus 0 at time 0, and this is at time t. We can evolve it. Let me put the indices here, which emphasize that we really do it at different times. So we apply this drive perturbation, we wait for some time, we measure time t, and we get the result. what is this? What is this?
This time, 0 t 0.
Yes, because when we measure, we always get, sigma x. What does it mean, measure, right? It means that we compute this. Right? That's what measurement means. And psi contains the derived times z. Yes?
How can you apply sigma, specifically sigma plus or sigma minus? It's not even unitary.
No, well, you apply sigma x.
Yeah, so
sigma
you
y
assemble a superposition.
and sigma y separately.
Okay.
Right, so now look at this quantity. This quantity, if we start with and we always in fact do that, we fix the number of excitations in our system, which is the same as fixed total sigma z. Now, look at these three operators which are written here. These three operators change the sorry, it was something else. Sorry, I need to do it slightly differently. I'm very sorry. I need to be more careful and do like this. I want start with the wave function, which is which I act the sigma x operator on my ground state first by some time, so that this is in fact 1 plus sigma x, well, I sigma x times I choose the time. Then I do the measurement as I explained before. I write here sigma x times t. Here we in the state, and what I get is here that I have, let's write it like this, 0, 1 plus I sigma x, 1 plus I sigma x psi. Okay, oh sorry, 0. Now look at, so this is at time t, this is at time 0, this is at time 0, but does not matter. So the only contribution that does not change the number of parts, total number of magnetization, are the pair products. Of course, there is also, so it's either this or that. All others, they change the number of particles, and therefore the result is 0. So what we get from this is the correlator, which is sigma x of t, sigma x of 0, well, maybe symmetrized because of this product. Of course, in this way, I can also do the measurement of, I can put here sigma y. Well, I can replace x by y here, and so I will measure the correlators, which are sigma y, sigma x, and all and all others, sigma y, and so on and so forth. So in this way, I can measure all possible correlators, and of course, as Anton asked me, get sigma plus, sigma minus from that.
There's also a minus sign
Yeah.
in the middle of this expression. 1 minus I sigma.
Yeah. There is also minus, so it's so that as a result, if it is I here, I will have always imaginary part. And so that minus I. So of course the result should be always real, and not measure imaginary quantities. So in this way, I can measure, in principle, in my system, not only these correlators, I can measure something very complicated, like just elaborating on this procedure, I can measure sigma plus, sigma minus, different sites, I, j, k, l, at different times, and so on. So all these correlators can be measured by in this way, and that gives us completely new tool compared to normal condensed matter, where all these most of these quantities are not available. And so that's basically, I think, enough for today. And so next time I will show you some experiments that we already did at Google, in which we used all this machinery, some of that machinery, to measure something interesting. So that will be sort of application of what I try to describe today. Not everything, because the things that with J1, J2 were not implemented, for instance, but some of these things we did. Okay, very good. Thank you. Any questions? Complaints?
Here I'm a little bit confused.
Yeah.
Up down there, it seems to me that you're measuring time dependent coordinates.
Yes. We always know the idea is always to measure time dependent.
Yeah, but there you're basically saying the
So what I was trying to describe, that in this way of doing the procedure, that is, I first start with my wave function, then I apply this perturbation, and then wait for some time and measure. I can basically measure any time-dependent correlation.
But the spatial correlation is just by...
Yeah, but nobody prevents me from, let's say, applying this perturbation at site I, and measure it at site j. So I can do everything. And that's exactly what we did in this.
Okay, so